So to summarize what we've seen about entropy, we could say that matter or mass likes to be dispersed in the most possible number of configurations or positions, and that tends to happen, and that maximizes this new term called entropy. Okay. Now let's talk finally about energy, and when we think energy, we think temperature, and more specifically, we might say that the average kinetic energy, Ke bar, is proportional to temperature. And whenever we think about this relationship, we always think about a Boltzmann distribution where the y-axis is fraction of molecules, the x-axis is kinetic energy, that's a Ke down there, and it looks generally like this. And what we see is that at one temperature with one average kinetic energy, there are a wide variety of kinetic energies at which there are some fraction of particles. Okay, now let's talk about this. So because that distribution is again about dispersing matter over energy states. Now what we've done here is we've taken a very small version of what we would call a macroscopic picture or a mole-sized picture, because we're going to have 3 atoms and they have 4 possible energy values, and we know that the total energy is 3 energy units. And then we're going to ask the question, which energy configuration has the highest entropy or the most number of microstates? And what we can see, so I've got the molecule or particle, wait, it says, well, let's call them atoms. Sorry for that. Either way works. So, but since I referred to them as atoms up here, let's refer to them as atoms down here. And let's say these atoms have a total energy of 3, in which case one of the particles can have an energy of 3. Well, then the other 2 must have energy of 0. So this is energy. And then there's also particle A, particle B can have 3, and particle C can have 3 energy units. So there are 3 microstates in which one of the particles has 3 energy units and the others have none. Then if we look at, and so we'll draw a line here, then we have 1, 2, 3, 4, 5, 6 microstates in which one of the particles has 2 energy units, one of them has 1, and the other has 0. And then we have 1 microstate when each of the particles, each of the atoms, has 1 energy unit. Now, according to what we've said about entropy, and which is the highest entropy state and which is the most probable, it will be the one with the most microstates. So, and what you can see is there's a 2, a 1, and a 0, so they fill the most different levels. The energy has been spread out over the energy states. So the 6 microstates is the most probable because it has the most microstates. Most probable, most microstates. And highest entropy. And what else? Oh, and so the energy is spread out the most. And what we could then say is the second highest entropy state is here because there are 3 microstates, and there's only 1 microstate where the energy is all in the same energy level. So interesting to think, again, entropy, dispersal of matter, can include dispersal of matter or mass over different, more energy states. Now, so we're at the end of our examples for this, and what do you have to know for the exam, right? Two things. One is, if you see a question like this on an exam, pick the choice with the most microstates. Pick the choice with the most microstates as having the highest entropy. So say you had pictures like this and it said which of these states has the highest entropy. You would pick the one with the most microstates. You would pick the one where the two bulb examples where the particles are evenly distributed, or the most evenly distributed if you have a variety of choices. And then two, if you're asked to do the distribution yourself, distribute the mass, the matter, over as many possible places, as many possible energy states as possible. So distribute matter over as many possible positions and or energy states as possible. And there's probably going to be something about this on the exam.